Hello, this is Professor Roman. Let's continue the lecture series in linear algebra. It's now time to talk about eigenvalues and eigenvectors. As we've seen, it's the invariant subspaces of a linear operator that provide the key to unraveling the structure of the operator, at least in the finite dimensional case, but in general as well. As we remarked earlier, the simplest non-trivial tau invariant subspaces of a vector space, if they exist, are the one-dimensional invariant subspaces. So the subspace generated by a single non-zero vector v. And these will be tau invariant if and only if tau v equals lambda v for some scalar lambda. In this picture we see then that the behavior of tau on v is simply either to expand or shrink v, or pointed in the opposite direction, expand or shrink. So the behavior of tau on this one-dimensional tau invariant subspace is very simple. And that calls for a definition. A scalar lambda is an eigenvalue, also called a characteristic value or proper value. I think this term, proper value, is an older term, not used as much anymore, for the operator tau if there's a non-zero vector v for which this equation, tau v equals lambda v, called the eigenvalue equation, holds. And in this case, v is called an eigenvector, or characteristic vector, or proper vector, of the operator tau associated with the eigenvalue lambda. It's important to emphasize eigenvectors must be non-zero by definition. If you allow the zero vector to be an eigenvector, then it would be an eigenvector for every scalar, because this would be zero on both sides, and that's not acceptable. So eigenvectors must be non-zero by definition. And it's convenient to pair these things together. The pair lambda v, where lambda is an eigenvalue for tau, and v is an eigenvector associated to lambda, is called an eigenpair. The set of all eigenvectors associated with a given eigenvalue lambda is not quite a subspace of v because it doesn't contain the zero vector, as we just discussed. But that's its only shortcoming. So if we toss in the zero vector, we do get a subspace. It's called the eigenspace for the eigenvalue lambda, associated, of course, with tau. And I'll use this notation, script e sub lambda of tau. So this is, in fact, the set of all solutions, v, to the eigenvalue equation, regardless of whether v is zero or not. So it's almost the same as the set of eigenvectors, but you have to throw in zero also. And just for convenience, when the operator tau is clearly defined, I'll probably just write e sub lambda for the eigenspace. The dimension of the eigenspace, e lambda, is called the geometric multiplicity of the eigenvalue lambda. There's no common notation for geometric multiplicity, unfortunately. So I invented one that I think everybody will understand, GEOMULT of lambda, the dimension of the eigenspace. Incidentally, there is another kind of multiplicity for eigenvalues called the algebraic multiplicity, and we'll discuss that later. So one needs to use the adjective geometric here, otherwise there would be confusion. The set of all eigenvalues of an operator, tau, is called the spectrum of the operator. And I'll denote that by SPEC of tau. Keep in mind that there's no mention of multiplicity, either geometric or algebraic, in the spectrum. It is simply the set of all eigenvalues without regard to their multiplicity. So I'm going to leave it to you to show that the eigenspace E lambda is in fact a subspace of V. The eigenvalue equation, of course, can be written this way. Now it's customary here to write t minus lambda. It would be more proper to write t minus lambda, and this iota is the symbol we're using for the identity operator, because this is supposed to be a linear operator, but one generally drops the iota or whatever symbol is being used for the identity and just write tau minus lambda. So this lambda is not really a scalar, it's the operator multiplication by lambda. In any case, the eigenspace then is the solution space to this equation, which is simply the kernel of the operator tau minus lambda. So in particular, if 0 happens to be an eigenvalue of tau, then this eigenspace E sub 0 is just the kernel of the operator. In any case, in the finite dimensional case, we can use the rank nullity theorem here to some advantage. In this case, the geometric multiplicity of lambda, this dimension of this kernel, which is the dimension of V minus the rank of the operator. This formula, as we will see, has some important uses. I guess the most overriding question now is, how do you find eigenvalues and eigenvectors? Well, we'll discuss that in a few minutes, but first I want to do some examples. C infinity of R is the vector space of all infinitely differentiable functions on R. And if D is the derivative operator, then D applied to, say, e to the 2x is 2e to the 2x, as you probably know. And this is an eigenvalue equation. It tells us that lambda equals 2 is an eigenvalue for the derivative operator with eigenvector e to the 2x. This is a common situation. Eigenvectors that are functions are often called eigenfunctions, and they're very important in applied mathematics and differential equations, and mathematical physics, and so on. In the same context, the second derivative operator sends the sine of x to negative sine x. So lambda equals -1 is an eigenvalue for d squared. and the sign of x is an eigenfunction. Here is a more sophisticated example from physics, which I don't know much about, I must admit. It's not my area. But if h of xt denotes the vertical displacement of a vibrating string with time, then the wave equation is this second-order partial differential equation. If h of xt can be factored, the variables can be separated, then this equation gives two ordinary second-order differential equations, both of which are eigenvalue equations. So we have two eigenvalues and corresponding eigenfunctions. Eigenvalues and eigenvectors appear in the theory of dynamical systems. And here's a simple example of a discrete dynamical system. Let's say that A is a complex matrix, n by n. This equation, x sub k equals ax sub k minus 1, gives this, if you think of x sub k as the state of the system at time k, at discrete time k, then this gives the relationship between the state of the system at time k and the state of the system at the previous time, k minus 1. If we start with an initial state vector x naught, then an easy induction shows that x sub k is a to the k x naught. So the state of the system at any given discrete time really depends on the powers of the matrix A. Now, you can ignore this. If C sub n has a basis, an ordered basis B, u1 through un, that consists of eigenvectors of A. This is unusual, but it does happen. We'll talk about this in more detail in the future. A basis of eigenvectors, it's called an eigenbasis. If that should be the case, and let's say then that u sub k is an eigenvector for the eigenvalue lambda k, so we have the eigenvalue equations here, and this is for all k running from 1 to n. Then we can write matrix A is of course its own representation with respect to the standard basis. This is the change of basis formula. This change of matrix representation formula. So this is the representation of A with respect to B, the basis, the eigenbasis. So we have this equation, and to simplify, we can set P equal to this matrix whose columns are the U's, and D equal to the matrix whose diagonal matrix whose entries are the eigenvalues. It simplifies this equation, then simplifies to this. Actually, this is hiding all the information, but it doesn't matter. It's the form of this equation that I'm interested in, because D is diagonal. And so x to the k, x sub k, the state of the system at time k, is a to the k x naught, which is now a to the k. If I raise this to the kth power, it's simply p d to the k p inverse. So it looks like this. And again, for simplifying purposes, we'll let P inverse x naught be this matrix, this column matrix. And so a little bit of matrix algebra shows that the state of the system at time k is given by this formula. This involves the eigenvectors and the eigenvalues to the kth power, and some constants, C1 through Cn, that do not change with time. Well, this system then is said to be stable when all the eigenvalues have norm less than 1, because then the powers lambda of the eigenvalues go to 0 as k goes to infinity. So the solutions, or the state of the system, tends to 0, regardless of the initial value. That's the stability of the system. But if any eigenvalue has norm bigger than 1, then the state of the system approaches infinity. This system is unstable. And finally, if some eigenvalue has norm equal to 1, but the other eigenvalues have norm less than 1, the system is said to be neutrally stable. And that is everything I know about dynamical systems. It's not much. I've never studied dynamical systems. I'm not a big fan of differential equations, so I apologize for that. But if you are, at least hopefully this will give you some direction which to look further at the relationship between dynamical systems or differential equations in general and eigenvalues and eigenvectors. So now we'll return to the world of algebra. In the finite dimensional case, which is the case we will be concerned with mostly, almost exclusively, the spectrum of an operator is a similarity invariant. And here's the reason. The eigenvalue equation looks like this. If we apply a coordinate map to both sides of this, that's an isomorphism, so this holds if and only if. This holds after applying the coordinate map. It tells us that this eigenvalue equation holds if and only if this eigenvalue equation holds. And so lambda v is an eigenpair for tau if and only if lambda and the b coordinate matrix of v is an eigenpair for the matrix representation of tau with respect to b. So here's a picture that describes the situation. We have a linear operator on V. We have various matrix representations for the operator that fills a similarity class. Now remember, these are matrices. They're also linear operators, so they have spectrum. They have a spectrum. The spectrum of each of these matrices is the same, and it is the same as the spectrum of tau. The eigenvalues for an operator are the same as the eigenvalues for a matrix representation of that operator. The eigenvectors are the corresponding coordinate matrices of the eigenvectors of tau. Let me say that again, just to be clear. The eigenvalues of tau are the same as the eigenvalues of any matrix representation of tau. And the eigenvectors of a given matrix representation, tau b, are the b coordinate vectors of the eigenvectors of the operator. So that's the content of this theorem in part. The spectrum of a linear operator is the same as the spectrum of any matrix representation of the operator. And the eigenvectors are the b coordinate vectors. So if we restrict this the coordinate map phi sub b to just the eigenspace, we get an isomorphism between these eigenspaces, the eigenspace of tau and the eigenspace associated with lambda, then the eigenspace of matrix representation of tau, same eigenvalue. Well, this means that if we have two matrices that are similar, and if lambda is an eigenvalue for those matrices, then the eigenspaces are isomorphic because they are both isomorphic to the eigenspace of tau. In particular, the geometric multiplicities are the same. So not only are the spectrums the same, but so are the dimensions of the corresponding eigenspaces. In other words, if we pair each eigenvalue with its geometric multiplicity, this set of ordered pairs is also a similarity invariant. The spectrum is, and so is this. This is more information than just the spectrum. The spectrum would just give you the eigenvalues. This gives you the eigenvalues together with the dimensions of their eigenspaces. So both of these are the spectrum and this set, which I call D sub A. There's no notation that I know of for this. Are similarity invariants, but they are not complete, neither one. To see that the spectrum by itself is not complete, we can just look at these simple matrices, the zero matrix and this matrix. Both of these matrices have the same spectrum. It just consists of the zero eigenvalue itself alone. It's pretty clear that the zero matrix has only the zero eigenvalue. But this one, we have set up the eigenvalue equation. A arbitrary vector xy equals lambda xy. Looks like this, and this has a non-zero solution when lambda equals 0, but the only solution when lambda is non-zero is the zero vector, which is not an eigenvector. So lambda equals 0 is an eigenvalue, but no other scalar is an eigenvalue. So these two matrices have the same spectrum, almost a trivial spectrum, but they do not have, I shouldn't say trivial spectrum really, because there are matrices that have no eigenvalues at all. So this is just say the zero set. But these matrices are not similar. and I'll let you ponder that. As to this collection of data about the matrix, the eigenvalues, and the geometric multiplicities, this is also not complete. I'd have to work just a bit harder. Here are two matrices, 4 by 4 matrices. The spectrum of each matrix is again the set containing only 0. And the eigenspaces are these two spaces. Same geometric multiplicity, two-dimensional spaces, subspaces. So these two sets, since there's only one eigenvalue, geometric multiplicity 2, this set D of A contains only one-ordered pairs, lambda equals 0, geometric multiplicity 2, in both cases. But these two matrices are not similar. One way to see that is to note that if A and B were similar, then A squared and B squared would be similar, and I'll let you sort that out. But A squared is not 0 and B squared is 0. And these two, a non-zero and 0 matrix, cannot be similar. One way to think of the eigenvalues of a matrix is a statistic for the matrix. That's a technical term from statistics. It's similar in this case to the mean or median of a set of, say, test scores. That's a statistic for the collection of all test scores. It's a summary information. The eigenvalues of a matrix give some information about the matrix, but not, in general, all information. They don't generally determine the matrix. We've just seen examples of that. So the eigenvalues, the spectrum, is summary data about the matrix. It loses some information in general, but it still retains a very valuable amount of information about the matrix. Even though the spectrum of a matrix is not complete, it still can be used, as we discussed some time ago, to show that two matrices are not similar. So here is an example. Here are two matrices. If you wanted to determine directly whether these matrices were similar or not, you'd have to figure out whether there was an invertible 3 by 3 matrix P for which B equals P inverse AP. An unpleasant task at best. But if we look at the eigenvalues, this is the eigenvalue equation for A. Actually, this is the eigenvalue equation for A. It looks like this. So the only eigenvalue is lambda equals 1. And the eigenspace is the solution space to this, is this two-dimensional subspace. For the matrix B, this is the eigenvalue equation. And the only eigenvalue is lambda equals 1, which is the same eigenvalue, it's the same spectrum for A, so A and B have the same spectrum, consisting just of the single scalar 1, but the eigenspace for B associated with 1 is one-dimensional. So let me try to get this back here again. Here's the eigenspace. For A, it's two-dimensional, same eigenvalue. This is one-dimensional. So even though the spectra of the two matrices are the same, the geometric multiplicities associated with the only eigenvalue are not the same, and so the two matrices are not similar. And that, again, is much more pleasant than showing directly that there's no matrix P, invertible matrix, for which this holds. Okay. So this is a good example of the value of invariance, even ones that are not complete. It's a fundamentally important fact that eigenvectors associated to distinct eigenvalues are linearly independent. This, by the way, does not require finite dimensionality. So suppose that lambda 1 through lambda m are distinct eigenvalues of a linear operator. Eigenvectors associated with distinct eigenvalues are linearly independent. So specifically, if lambda I vi is an eigenpair for each I, 1 to m, then the eigenvectors v1 through vm are linearly independent. These are eigenvectors associated with distinct eigenvalues. It follows, as we'll see, that the eigenspaces are strongly, essentially disjoint. And so this direct sum exists. The sum always exists, as we've discussed, but the sum is actually direct. Now, this doesn't say that this sum is equal to all of V. Sometimes it will be, sometimes it won't. We'll talk about that later. But at least the sum is direct. And you should be able to get a sense there that this is the beginning of a very nice decomposition of V. This may not be a complete decomposition. As I said, this may not equal V, but it at least decomposes a subspace of V into one-dimensional tau invariant subspaces. So, as to proof, let's suppose that we let S be this set of eigenvectors associated with these distinct eigenvalues. And suppose to the contrary that this set was linearly dependent. Well, we can look around for the smallest, the shortest linear dependency. So more formally, we can find a non-empty subset T of S of smallest size that is linearly dependent. And just by re-indexing, if we need to, we can assume it's V1 through Vk. So these are linearly dependent, but no subset of this, no proper subset is linearly dependent. So there are now non-zero scalars. We couldn't say non-zero unless we found the smallest type of subset here. There are non-zero scalars for which this linear dependency holds. Now, from this point, we do two things. We apply tau to this equation. So tau of v1 is lambda 1 v1 and so on. We get this equation. The second thing we do is take this equation and multiply it by lambda sub k for a fixed k. So that looks like this. So we now have these two equations, and we can subtract. And that gives us this equation. Now k is bigger than or equal to 2 because this is a linearly dependent set. Singletons are not linearly dependent unless it's the zero vector, but these are eigenvectors, so we don't have any zero vectors. So k minus 1 is at least equal to 1. It's 1 or bigger. So this equation, this difference hasn't totally disappeared. But what we have now is, since the lambdas are distinct, lambda 1 minus lambda k up through lambda k minus 1 minus lambda k, those are all non-zero. The a's are non-zero, so the coefficients are non-zero, and we have a linear dependency that's shorter than the one we started with. And that's not possible because of the way we picked t. This is the shortest linear dependency. It's a linear dependency with the fewest number of terms. But this one has one fewer term. We have a contradiction. So this set, in fact, must be linearly independent. This may take a rereading a few times. It's a traditional proof, very common proof by contradiction, well worth absorbing completely. Part 2 of this theorem says that these eigenspaces are strongly essentially disjoint. So here is the family of eigenspaces. If a non-zero vector in one of these spaces or subspaces was also the sum, let's call it, let's see, what did I call it here? V sub I. So this should be V sub I. So if V sub I was a sum of vectors from the other subspaces in the family, this would violate the strong essential disjointness. If this did happen, then we have a contradiction to the linear independence of these vectors. So it can't happen. So no vector in one of these subspaces is a sum of vectors in the other subspaces, and therefore this family is strongly essentially disjoint, and so the sum is direct. Now we come to a relatively famous theorem called the spectral mapping theorem. Suppose V is a vector space over field F and tau is an operator on V. If P of X is a polynomial over that same field F, then P of tau is a linear operator. Tau squared is a linear operator, tau cubed, any power of tau, any scalar multiple of tau is an operator, any sum of such. In other words, any polynomial in tau is a linear operator. We're going to spend a lot of time discussing polynomials in an operator. What about the spectrum of P of tau? It is very strongly related to the spectrum of tau. And that's what the spectral mapping theorem tells us. It's strongest, however, when the base field is algebraically closed, so such as the complex field but not the real field. Just by way of notation, and this is not surprising, if S is a set, P of S is the set of all P of little s's, as little s ranges over S. So we can take P of the spectrum of tau, and it's P of lambda, the set consisting of all P of lambdas as lambda ranges over the spectrum. So here's the spectral mapping theorem. V is a vector space over F, and P of X is a polynomial over F. Then for all vectors V, tau V equals lambda V, the eigenvalue equation, implies P of tau V equals P of lambda V. In other words, if V is in the spectrum, if V is an eigenvector for lambda, lambda is in the spectrum of tau, then P of lambda is in the spectrum of P of tau with the same eigenvector. So if I take the spectrum of tau and I apply the polynomial P to every eigenvalue in the spectrum, I will get eigenvalues for P of tau. I may not get all the eigenvalues for P of tau, but I do get eigenvalues. Loosely speaking, I guess you could say that applying a polynomial sends eigenvalues to eigenvalues. When F is algebraically closed, this inclusion becomes equality. So the spectrum of P of tau is precisely the set you get when you apply P of X to the eigenvalues of tau. P, the polynomial P, sends the eigenvalues of tau to the eigenvalues of P of tau. And here's the proof, or a proof. If, for part one, if tau V equals lambda V, or V is non-zero, then we can continually apply tau. So tau to the kV is lambda to the kV for all k bigger than or equal to 0. And so if P of X is any polynomial, P of tau V is equal to P of lambda V. This is just basic algebra. So P of the spectrum of tau is contained in the spectrum of P of tau. Okay, that's just a very simple algebra. Part two is a little more work. If we take lambda in the spectrum of P of tau, we want to show that lambda is P of some eigenvalue for tau. Well, this is the eigenvalue equation for lambda. P of tau minus lambda V equals 0, and V is non-zero. Now, here's the point. Since the base field is algebraically closed, we can factor this polynomial, P of X minus lambda, as a product of linear factors. The R sub i's belong to the base field. Now, V is non-zero, but when we put tau in here for X and apply it to V, we get 0. That's this equation. So, if we start with our non-zero V and we start applying these linear factors with x replaced by tau. So this is the last one, tau minus Rn v. I don't know whether that's 0 or not. And then I apply tau minus tau minus Rn minus 1 to that previous vector. Still don't know. But when I get all the way down to here, I know it's 0. So the first equation, non-zero, the last one, 0. So one of these vectors is the last non-zero vector. The next one is 0. From then on, they're all zeros. So let's say that this vector, which I'll call W, this is a partial product, tau minus rk plus 1 up to tau minus Rn v. This is the last non-zero one, which means if I hit this with tau minus rk, I get 0. Well, what does this say? It says that W here, non-zero, is an eigenvector for the eigenvalue r sub k. R sub k is an eigenvalue of tau with eigenvector W. In other words, R sub k belongs to the spectrum of tau. But R sub k is a root of this equation. And so P of R sub k is equal to lambda. Lambda is P of R sub k, and R sub k is in the spectrum of tau. That is exactly what we wanted to show, that lambda is a polynomial in some eigenvalue of tau. And that's the proof of the spectral mapping theorem. One last item, and that concerns base fields and the spectrum or spectra of a matrix. Matrices do have one advantage over linear operators. I'm talking now in the finite dimensional case. Theoretically, we can go back and forth between the two, but there is an advantage to the matrix point of view. It's easy to change the base field of a matrix. All we do is declare the change. So if A is a matrix and its entries are in a field F, and if K is another field containing F, we can just declare that the base field of A is going to be K instead of F. Just as a simple example, here is a matrix. This is a matrix over the rational field because the entries are all rational, but it's also a real matrix and it's also a complex matrix. We can decide what we want the base field to be. As long as it contains the entries of the matrix, it's up to us. So we can choose the base field in a suitable way depending on the situation. Specifically and in particular, we are going often to think of a real matrix as a complex matrix that happens to have real entries for the obvious reason that the complex field is algebraically closed. So we gain some machinery, some tools, such as the fact that every polynomial splits when we work in the complex field. So I'm going to I refer to that as upgrading the field from the reals to the complex, or from F to a larger field, K, containing F. There is one problem with this that we have to be aware of, and there's no free lunch here. If you do an upgrading, say from real to complex, you split some polynomials and you learn some things. Those facts that you learn may not downgrade. If you then decide to downgrade the base field back to R, you may lose some of those facts. Okay. For example, the existence of eigenvalues, just because a real matrix, when you think of it as a complex matrix, has eigenvalues as a complex matrix, doesn't mean it will have eigenvalues as a real matrix, and we'll discuss that more in appropriate time. So upgrading can provide very important information about the matrix that doesn't necessarily hold if you decide to downgrade back to the original base field. But the upshot of this discussion now is that a given matrix has lots of different spectra depending on your choice of base field. So if A is an n by n matrix, and if K is any field containing the entries of A, then the K spectrum of A, which I'll denote this way, notice the subscript K, is the set of all elements of K for which the eigenvalue equation holds for some non-zero vector in K sub n. So for example, a real matrix has a real spectrum, but it also has a complex spectrum. But the complex spectrum only makes sense when you think of A as a complex matrix. If you think of A as a real matrix, then there's no such thing as a complex spectrum, because the eigenvalues have to be in the base field, they have to be real. So this is something worth pondering until it makes perfect sense, because it will be something that we use frequently to study the structure of finite dimensional linear operators.